Oh, yes.
Thank you, Siva. So we're going to have Kolya Malkin. Kolya is an assistant professor at Edinburgh, and he was a postdoc in my lab for many years. Forgot how many. He's been incredibly productive and has pushed the agenda in my group on probabilistic inference, amortized inference with neural nets and so on. And I guess he's going to talk about related things today. Take it on.
Thanks, Joshua and Siva, for inviting me. It was 3 years, by the way.
Thanks.
Right. So I will try to bridge two areas which have the property that everyone in the room probably works in some form on one or the other. One is probabilistic machine learning, and the other is LLMs. After all, that's the topic of the workshop. Now, this workshop has been full of very interesting hot takes over the last day and a half, and I hope to contribute to that chain of thought. There are a few big ideas in LLM research in the last few years, and many of them fall into the breaking of the simple paradigm that you take a language model, you prompt it, and you get an answer. So instead, we do other things with language models, like asking them to perform some other operations based on the prompt they receive before they give the answer they want, such as doing chain of thought, using tools, searching the internet, and so on. Especially in the context of so-called reasoning or acting in formal environments, there are efforts to train language models on synthetic generated data. The principle that verification is much easier in generation, which shows its face in many ways in computer science, has now been used to self-improve, or to improve LLMs, or to use them to improve themselves. And of course, there is reinforcement learning, where language models are improved with feedback derived from human input or from input of other machine learning models. So what's the place of probabilistic machine learning in the context of these developments in the use of LLMs? What can ideas from probabilistic inference in latent variable models do for the LLM field? And what does this all have to do with safe AI? Well, let me first fix the size of the slides. And I will use this from now on because the clicker does not do this quite as I wish. There we go. So I hope to shed some light on that question and give a few opinions. Before continuing, I'm not really an LLM person, not an LLM expert, as they now say, but I have worked on probabilistic inference for a while and on generative models, more in continuous spaces actually than in discrete ones lately. So I think some of what I'll say is somewhat upstream of the frontier of LLM research. So when we want to illustrate a proof of concept for a new algorithm, we often do it in the case where we see it in a simple example with a smaller model and really try to understand how it works. And that's the approach I try to take. But of course, in real deployments and in frontier models, things have moved far ahead in terms of applications to specific problems and tricks and practical considerations. So do forgive any references to things that in the LLM world may be considered ancient, the 2023 and earlier. And of course, thank you to all collaborators. I'll have some references throughout my work in this beautiful pink color, others in the other color. So here's a brief summary of what we'll do. So I'll introduce what amortized inference is in machine learning and how we can use amortized inference and probabilistic ML for robust and safe AI. And I will motivate what will come in the rest of the presentation by giving some examples of latent variables in language models. Then the second part will be about two recent works that I was a part of on amortized inference under language model priors. One for reasoning or chain of thought as a probabilistic inference problem, and the other an application to red teaming and safety fine-tuning. Then the third part will be more speculative, and I will give some ideas about how to use amortized inference, now not over text, but over symbolic structures, but using text models as a prior, to mine inaccessible knowledge from foundation models, language models specifically, and end with a summary of all the hot takes. So first, amortized inference. By the way, please, if there's a pressing question relevant to what's being said, just raise your hand and try to stop for that. Right, so this is, forgive me that this is such review. The traditional view of a latent variable model is that you have a probabilistic model, a joint distribution over some variables. Some are observed, some are hidden, latent. We see only the observations, which may come in a sequence or a set or something of the sort. And the latent variables participate in the generation of those observations, but we don't observe them. And the problem of probabilistic inference, or inferring the posterior distribution, is to figure out what the latent variables are when we see the observations. And an intuitive view is that this is something we do all the time when acting in the world. When we talk to someone, we infer their latent intentions. When we see an image, we understand what objects are in it, and so on. So the problem of probabilistic inference is to sample latents in a model given the observations. And by Bayes' rule, that posterior distribution is proportional to the product of a prior over latents with the likelihood that those latents produced the observations that we saw. And amortization, this is the only case where I have American spelling by mistake, is when we fit a parametric model to sample the latents given the observations. This parametric model may take any form. In our case, it'll be a neural net, specifically a language model or a reinforcement learning agent. So when we fit a neural net to predict what the latents were when we see observations, we get a model which can generalize to observations that we didn't see during training. So in this way, we've amortized over observations the cost of figuring out what the latents are for any new given set of observed variables. Now, these kinds of models appear everywhere in machine learning, and just to prime everyone's mind, I'll remind a few cases in ML where they come up. So in classical machine learning, we have mixture models where we have a latent mixture component, and each mixture component generates samples from a distribution in a chosen family. A simple neural generative model is an autoencoder, or a VAE, where we have a latent variable Z with fixed distribution, and there's a decoder or generator which produces samples. We have Bayesian neural nets where we have latent parameters which generate a function mapping observations to inputs to outputs. So in those last two cases, actually in all three of these cases, typically we model the distributions with something simple, not requiring neural nets like Gaussians. For things more relevant to language and with symbolic structure, we've got topic models where the generation of a document is modeled by a topic vector representing the mixture of groups of words which are present in the document, or a probabilistic grammar like a probabilistic CFG, where the latent variable is the tree by which the surface text is generated, and each node has probabilities of expanding into child nodes. And the observation is just a sequence of terminals, sequence of leaves. When in each of these models we see the surface form, or see the observed data X, and we try to infer the latents Z, which participated in their generation, we can view this as producing a kind of explanation for the data. And this explanation can be more or less meaningful as prescribed by the structure of the generative model. So when we have a context-free grammar, and Z is the parse tree generating X, the sentence, then parsing is inference of the latent variable, the tree that generated the sentence. Similarly, if our latent represents object structure in an image, then sampling the posterior is recognizing the objects present in the scene. We additionally need to sample posterior distributions as part of the training of the models themselves. So In the EM algorithm, which we can use to train such algorithms, the E step involves sampling the posterior distribution over latents given observations. In training neural generative models end-to-end, we can optimize variational lower bound on the likelihood, which also involves the same posterior distribution. So sampling posteriors is finding the latent explanations that are responsible for observed data. And the problem of amortized inference is that of doing it by fitting a model to generate those explanations. Now, here's a question. What if that latent variable is actually language itself? So Z has the form of text. That's interesting because many interesting explanatory variables which we can verbalize when we describe data that we see are symbolic, like they are causal structures or they're programs which generate answers given inputs. And so they're representable in language or something similar to language. So when we describe the world and when we think about the world, we do so symbolically. And the symbolic structures we work with can be converted into language form. On the other hand, probabilistic inference, so sampling distributions in discrete and compositional spaces such as language, is a very hard modeling problem. It's not something like Gaussians where there are two parameters which we can do gradient descent over. And it's especially difficult to sample in such spaces in a way that's efficient, so not running long MCMC chains, which asymptotically converge but are really slow and are hard to do in discrete spaces, and also asymptotically unbiased, meaning that rather than getting a cheap approximation to the posterior distribution, we want something that captures the full uncertainty over latent explanations for an observation. And that problem is particularly hard when the thing we want to sample, the latent explanation, is something discrete and structured, like language or other discrete compositional structure. Why are we interested in these sorts of questions, like sampling latent explanations in the context of safety? Now, I'll speak first at a high level, and we may see some instantiations of these things later on. Well, agents that act in new and unknown environments where some properties of the environment are unknown need to be aware of the uncertainty present, say, in the reward, in the transition model, and so on. So if they want to act in a way that's robust and in the worst case will still not kill themselves, they need to model the uncertainty over explanations of the transitions they observe when they act. So we want to minimize our risk in environments where some properties are unknown, then we should model the full distribution over what the environment could act like. So we want latent explanations for our environments. That includes things like causal world models and the like. And posterior sampling problems appear in more straightforward safe RL settings, like just sampling a collection of trajectories that a robot might follow, given that they can't pass through some obstacle area. So in all these settings, we want to sample constrained or posterior distributions over some variables. Now, what about LLMs? LLMs have a lot of world knowledge, and as we'll come back to in the last part of the presentation, they can be useful as priors over things like symbolic world models. And they are perhaps more useful in that capacity than as faithful to world knowledge reasoners. And they're more useful, and they can be useful as well as the inference models themselves. So we can fit language models which perform inference over language-structured latent variables. A question?
So if you use an LLM as a prior over some of the reasoning weekend, there will be some kinds of reasoning which have more synonyms than others.
Which have more
synonyms.
Yes.
So there's a worry that this kind of contaminates your sense of like what the latent probabilities are over the kind of more kind of high-level actual reasoning. Will you talk about how to get around that problem?
The question is that I'll just repeat the question for the sake of online. The question is, if you have a prior given by LLM over some language variable, and some things expressed in language have many synonyms, and that kind of contaminates the prior because it gives a lot of total mass to those synonymous ways of saying the same thing. That's certainly a good point. you would hope to structure the problem in such a way that you care about the total mass captured by all the synonymous ways. The ways that can be done in specific cases are to consider some higher level symbolic structure, which is then converted into language form by deterministic mapping. For example, let's say you're doing inference over simple causation relationships. So you can take a causation relationship and write it as a string. So there's one way to express that. So the prior is unnormalized, but it's just the restriction of the full LLM prior over the set of all strings which are expressions of such causation relationships. Now, a small digression on intractable inference in language models. When we have a language model that generates text left to right, so everything I say is applicable to diffusion language models as well. Let's just consider left to right because it's more familiar. It can compute for us the likelihood of any string when by factorizing it as left to right next token probabilities. And we can sample such probabilities extractively left to right. But sampling even from very simple variations of this distribution becomes an intractable problem. For example, we can't sample from a tempered distribution, like raising that distribution over n words to a power. In particular, finding the argmax. We can only approximate that with things like beam search or greedy decoding. We can't sample text of a given length, so marginalize that distribution conditioned on having end of text as the n plus first symbol. We can't tractably condition the distribution given by the language model to have a given suffix, so end in a certain string. Prefix is tractable, suffix is not. Or lexical constraints like avoiding or using certain words. Or what's important in many LLM applications, sampling the product of a language model with a reward or a verifier score. We can only approximate all these things, for example, by prompting the language model in a clever way, hoping that it satisfies the constraints. Even if it does happen to satisfy the constraints, those samples we get might be biased with respect to the true constrained or posterior distribution. So with language models, we immediately, even with very simple probabilistic queries, run into a problem of intractable inference. So the idea that I want to suggest is we should think of a language model as a policy in the sense of RL, or a proposal in the sense of Monte Carlo, and we should train it, and fine-tune it, to sample from these desired distributions. So that means perform amortization. Use the language model as a parametric model to sample these intractable posterior distributions. That's take number one for what we should do in probabilistically principled LLM usage. And we'll see some instantiations of this in just a second. Let's see how a reasoning problem in language can be seen as an instance of such intractable inference. So let's say we have a prefix and a suffix, which are two events that happened in a short story. Now, what happened in between? This is a toy example of reasoning that humans are very good at doing. On the level of images, imagine filling in a video between the scene on the left and the scene on the right. Now, we can view this as sampling a posterior distribution over the sentence that is in between this prefix, the cat was hungry, and the suffix, cat is sleepy, where the prior distribution is given by a base language model. So in this latent variable model, we have a prefix x and a suffix y, and x generates y by means of an intervening latent variable z. And the posterior distribution over z is computed by Bayes' rule. It's proportional to the joint distribution over the whole sequence. First the prefix, then the infilled, the intermediate sentence, and then the final sentence. So finding that middle sentence, or infilling, is a problem of sampling a posterior distribution. And as we'll see a bit later, chain of thought reasoning for answering a prompt to answer kind of question is also a special case of that. So this kind of simple reasoning in language is a posterior inference problem. What else? A chain of thought reasoning, like classifying text into labels or doing simple mathematics problems where we have access to tools, In all of these cases, we have an intervening latent variable. It may be a chain of thought, it may be an infill sentence, or it may be a sequence of applications of external tools, like a calculator. Just to list a few. In retrieval-augmented generation, the latent variable is a set of documents that we retrieve. So conditioned on a query X, we retrieve Z, and then we generate Y. In tool use, Z is a sequence of tool calls. In program synthesis or proof synthesis, the latent variable is a probabilistic program, or just a program, or a proof, which is also a program, which, when given input X, will produce the answer. In hierarchical prompting models, where we want to discover a sequence of LLM calls which will generate the answer, the latent variable is the sequence of prompts we apply, and then the calls to the LLM with those prompts are like tools themselves. And of course, in the approaches to long-form text generation, which have been around even before LLMs, latent variables such as plans or plots together with characters have been used to guide the generation of a long-form text with some latent structure. So inference of latent variables actually allows us to interpret many different ways that LLMs can be used, beyond just predicting Y from X. Now, given this, you could ask, why not just prompt? And one answer to that is, well, you can prompt if your model is good enough. You don't have to train anything, sample any unbiased posteriors, just prompt the model the right way. And if the model is big enough, then it'll do it correctly. Now, I really like this example. This was a GPT-3. I think a modern model will do a little better than that. But it illustrates well the kind of interaction that a failure to infer a latent variable by a model can lead to. So I ask the model how I plan a holiday in Scotland, and starting with arriving in Edinburgh, and it tells me to take a train to England. So if you think about what's going on here, you have to infer the user's latent intentions. So if the user says they arrive in Edinburgh, they probably want a holiday in Scotland, not in England, because there's a bigger airport in London. You'd probably fly there if you wanted to. But the data to infer that is quite sparse in the training set, probably. So the model has to be very big and has to know a lot about the world to do this well. So modeling posteriors well requires a lot of data that's not necessarily specialized to the task that we're going to use it for. Now, okay, well, maybe we can train a model that's big enough and has seen enough data to be good at what we prompted for. But even then, there are some failures. Here's another recent work which considered this problem. Let's take a description of a graph which is expressed in language. There are some rooms, and some rooms are connected to other rooms. That's just a graph. And then we ask the model to perform some simple graph-related queries, like finding shortest path from one vertex to another. And we give in-context examples where we show how a simple graph algorithm is executed step by step. And we see that the model is quite good at converting the description of the graph into some symbolic form. So it could sample the adjacency matrix exactly, almost perfectly. But it's quite bad at actually executing the algorithm. So the model can kind of understand the symbolic structure that's expressed in text, but it's very bad at reasoning within that latent structure. So it can't actually execute the graph algorithm in text. So just like the well-known idea that the number of parameters needed in the model to add n-digit numbers is super exponential in n, we can imagine that for symbolic reasoning tasks, the model and the data used to train it grows way faster than we may want. These models are, in a way, they're skipping the prediction of the latent structure, like what the user wants or what the adjacency matrix of the graph is, and modeling the posterior predictive. So just trying to do all the reasoning within the language. We can do better than that. Foundation models have some understanding of these latent variables because they can parse them out of the text. But querying for that knowledge, as we've seen, can be an intractable problem of probabilistic inference. So let's move on to something a little more technical. I'll now tell you about a couple of applications of amortized inference with language models, one to chain of thought and one to red teaming. Now, just a quick digression. I've said that amortized inference is when we train a model to sample a posterior distribution over some variables. Now, specifically, the variables we're interested in will be language, and so the parametric model we use will itself be a language model. And so we're in the setting where we're trying to sample latent variables which are generated step by step by taking a sequence of actions like appending one word at a time to the thing we're generating. Here are frameworks for reinforcement learning for doing probabilistic inference come in. You can vastly generalize the setting of using a language model to sample a posterior distribution over text to include many settings when you have a sequential decision-making process, which is generating some object, and you receive a reward for the final object you generate, and you train the model so that at convergence, it samples the distribution with probability proportional to the reward received. So there are different ways to express these frameworks. One is that of generative flow networks, or GFlowNets, which is one I contributed to developing in the last few years. So it includes all at once autoregressive models, diffusion models for any sequential decision-making decision-making process which generates some object. Just for example, suppose we want to generate a causal graph and parameters of the mechanisms. We can think of an agent that begins at an empty causal graph on the left and then takes an action to add in an edge, and then takes another action to add an edge, and then samples the parameters, and finally receives the reward. So this decision-making process expresses the sampling of a causal graph with parameters. Just the same, autoregressive sampling is a way of sampling text. Diffusion, the generative process of diffusion models, is a way of sampling things in continuous spaces like images, or discrete diffusion, also text, and so on. So I like this language because it allows us to talk about unified RL algorithms to perform inference where the generative process, that is to draw the sample from a posterior, can be seen as an agent in some sequential decision process. So now to LLMs. So this allows us to abstract away the fact that the posterior is a left-to-right language model. It could be anything else, like a diffusion model or a right-to-left model if you really want. So we want to sample a posterior distribution over some language variable Z, given maybe if it's infilling X and Y. So let's fine-tune the base language model, which can just unconditionally generate text, to sample from that posterior. So that model will, possibly conditioned on X, generate Z, receive a reward, which is the joint likelihood under the base model X and Y, which we saw that posterior is proportional to, and use that reward to update its parameters. And we repeat this. And at convergence, we would like that the model we've trained samples proportionally to the joint, so samples the posterior distribution. Yeah. Question? One slide. This one.
Yeah, I'm just curious about, you have inference as control there, and I think of that just as adding a optimality node in some probabilistic graphical model. What's the relation to the GFlowNets?
Control as inference, inference as control. I could give an answer that's somewhat technical, which will fully answer your question in the continuous space setting. Maybe we can do it on the whiteboard after, if that's fine. Question?
Well, first, a question from the earlier section. Yeah. To what extent is there clear evidence that sampling better from the posterior, like in this case of doing temperate sampling, which you point out as intractable, to what extent does doing that better actually help us with downstream things that we care about? Like, what's the empirical motivation for why we shouldn't just say, well, our current sampling methods are good enough or something?
The question is, why do we actually need to sample the posterior well? I don't know if you have a particular setting in mind, but say if we're sampling posteriors over chains of thought. As we'll see, sampling from better approximations of the full posterior will generalize better to new examples than, for example, learning to sample the argmax or just simple prompting or doing supervised fine-tuning on a few chains of thought. So we see this empirically in a variety of settings. I think in general, if we are going to model a posterior and then take samples from that posterior and then do something with it, so model a posterior predictive by, say, Bayesian model averaging, in general, there are cases where, for example, modeling the argmax, a point estimate of the posterior, is better than a Bayesian approach with a poor Bayesian approximation. But at least in theory, the thing that minimizes empirical risk should be to marginalize over the full posterior. So if we can amortize and model it well fully, we should do that. We can move on. Okay, so once we've trained such a model, we can use the learned policy, which samples Z, for a new X. In this way, we've learned to do the reasoning that follows X and ultimately generates Y in a demonstration-free way. So we have not seen any supervised examples of Z, but we've just discovered them through the reinforcement learning. Now, in particular, these algorithms, GFloNet or MaxNTRL, can work off policy, meaning that we can take advantage of interesting reasoning chains Z when we have them, add them to a buffer, say, and use that to improve our learning, rather than on-policy methods, which only use the current iteration of the model to generate the training data. Right, so what happens when we do this? Now, before I show some results, I just want to say that there are other methods than GFloNet or MaxNTRL for doing this. A few that have appeared in recent work, one based on MCMC, hybrid approaches that combine MCMC and amortization, like twisted sequential Monte Carlo. Distilling the language model into a tractable model like a probabilistic circuit or HMM. And all of this generalizes to diffusion models as well. So this is not the only way to solve this intractable sampling problem. You see different phases of these results in a variety of recent works. I should also point out that some recent work on self-improvement of language models, where the model is prompted to discover reasoning chains that lead to the right answer, and then reinforces the ones that do so, can be seen as a kind of hard rather than softer probabilistic version of this. So when we don't have likelihoods, we can still sample, see if we got the right answer, while not seeing the joint likelihood, and try to increase the likelihood of the chains that led to the right way. So in a sense, the standard RL fine-tuning, which tries to maximize the reward, is to test-time search methods, is what amortization by entropic RL, like what I've just talked about, is to Monte Carlo sampling at test time. So that's this. We have this analogy. Right. So just to show some results. So once we've trained that model that samples a reasoning chain given an input, we can use it to draw samples of reasoning chains, predict the answer. And this way, we not only get diverse reasoning chains for an answer, we also model uncertainty over the possible answer and the reasoning chain that led there. So I have to show some results. So on the left side, we have that simple subjectivity classification example that I showed. If we do supervised fine-tuning on a collection of prompts which explain the answer given the question, we, of course, improve over a base model. But if we do the full Bayesian posterior by such RL amortization, we do even better. And in particular, we do better when there are very few training samples, showing the optimality of being Bayesian when you have high uncertainty over what the correct way to reason is. Now, you improve even further if you do an EM step, so you update the generative part of the latent variable model. This corresponds to training the language model, which then predicts the answer y, given x and the reasoning chain set. The same is observed in the case of simple arithmetic with where the latent variable corresponds to a sequence of calls to an external calculator tool. So what's interesting here is that sampling the Bayesian posterior outperforms doing a reward maximizing RL, in this case PPO, especially in the out of distribution setting. So if you learn to just find the reasoning chain which, the one reasoning chain which is most likely to yield the right answer, you overfit to your training inputs X much more than is the case when you model the uncertainty over the sequence of reasoning steps which lead to the answer. I'll probably, in the interest of time, skip various other intractable inference problems you can solve this way. So yes, this is great, but it does not solve some problems. When we do this kind of posterior inference, we don't address any limitations of the base model itself, which is used to compute the joint likelihood. We have problems like if the reward model is too simple, the posterior will only be as good as that. And for example, language models which try to do tool use for arithmetic are often very happy to perform cancellation when they see a negative number and another number which can cancel it to make 0. So 1 minus 9 minus 8 is minus 16. But the model sees this and it's eager to take minus 8 and add 8 instead because that'll cancel. And humans, of course, have similar biases. When we're doing some calculation, we want to cancel everything and hope we get a nice theorem in the end. But if a reward model, which computes something proportional to the posterior over tool use sequences, calls to eval, likes this, then our posterior will like this too and we'll get the wrong answer. Then, of course, RL fine-tuning is much slower than supervised because we need to explore to discover what the good reasoning chains are. Of course, off-policy techniques can take advantage of the same reasoning chains that can be provided in supervision too. And what I've shown has considered task-specific models, not universal ones that rely on instruction. A few works since the paper from which I just showed the results that have pushed this in a few new directions. One considered a constrained language model as a diversity-seeking policy. So in an environment where you do some combinatorial manipulations like stacking blocks or solving a Rubik's Cube, you use the language model as the policy which generates a text description of the next action to take. And here again, you can train it in the same way to sample the posterior distribution over sequences of text instructions conditioned on solving the puzzle. Another paper, this one ICML last year, applied this approach to extracting simple temporal causations from data sets, where the language model is used to score the sequence of applications of these causation rules through time. And in one preliminary study, we have used this proof synthesis, where a proof can be thought of as a program that takes premises and transforms them into conclusions by passing through a sequence of intermediate proof states. And we aim to infer the posterior distribution over that sequence of proof tactics to use to pass through the sequence of states until we reach the target which we want to prove. What's missing in all this? Well, we can do reasoning in language, but we're missing memory bottlenecks, high-level abstractions, and all the things that humans do when they reason. We're missing interactivity, so we don't query users for feedback, and we don't consider adversarial settings. On the other hand, the kind of probabilistic fine-tuning we do may be less prone to reward hacking or over-optimization that we get when we try to maximize a misspecified reward. Grounding in world knowledge and multimodal models would also be interesting to consider. Right. A very recent paper, I just added this, came out a few weeks ago, suggests that recent very large models seem to be even better probabilistic priors for reasoning. So here, an EM approach with Monte Carlo and prompting is used to self-improve a language model, using Monte Carlo and prompting as the posterior, so no RL fine-tuning for amortization. And in ongoing work, on which we already have some preliminary results, we try to apply the methods I've described to this setting as well, just with newer and bigger and better language models. Now on to red teaming. Yes. So as an application that's more directly relevant to safety, we can try to use methods of RL fine-tuning for amortized inference to attack models to say something we don't want, and ultimately use that to improve those models. So it's probably familiar to most, but the problem of red teaming is the following. We have a target model or a victim model. We want to prompt it in such a way that it generates an answer and response that satisfies some criteria of toxicity or of undesirability. So that's the victim model, and the attacks on the left are something we want to discover. And we're going to train a model to generate those attacks, hoping that it finds attacks which do indeed generate harmful responses. That's the problem we want to solve. So how can we treat this as a problem of probabilistic inference and solve it by amortization using reinforcement learning? Well, what are the players and what's the objective? All right, so we have the attacker model, that's p theta. We have the target model, which generates answer y given x. We have a probability that that response that's generated is toxic, which may be scored by an auxiliary classifier, which we've taken off the shelf. And we have some base language model, which we're going to use just to ensure that attacks are close to natural language. So one way to formulate this problem probabilistically is as a KL-constrained reward maximization problem. So we want to discover attacks x so that the probability that the response that's generated by the target model is toxic is as high as possible, but under the constraint that the attack model should be close to the base model of natural language. So the attacks should not deviate too much from some reference language model. So we have this KL-constrained reinforcement learning problem, and it's equivalent to sampling from this posterior distribution. So it's a product of base language model, maybe tempered somehow, with this expected log probability of toxicity. So C is, say, a toxicity label. So we have to sample from this posterior distribution. Now, all we have access to initially is that reference model. So sampling from something like this is intractable to begin with. So let's do this pipeline. So let's fine-tune our base language model to sample from that intractable posterior. So the mechanics of this are our policy generates potential attack, create a plan to save something from a casino. The target model starts giving an answer. It gives an answer. Our toxicity classifier says if it's toxic or not, and that, by the formula from the previous slide, provides a reward. That's used to update the parameters of the model, and at convergence, we will be sampling proportionally to that reward, which we wrote down in the previous slide. So as a secondary step, we can perform something that's actually done in a lot of recent LLM-based pipelines. We don't rely on RL as the ultimate way to derive the model that we want to create. We use it as an intermediate step in discovering interesting attacks. And then we finish this off with a step of supervised fine-tuning on the attack prompts that we discover. So this entropic RL fine-tuning can be used just as well as a search model as a posterior model itself. So what we end up with in either case is a model that generates prompts which are both likely to induce a toxic response and which look like natural language according to the base language model. We can then do a third stage where we safety tune the target language model, meaning we prompt it with the attacks that we discovered, and fine-tune the target model to refuse to answer those. So what happens with this pipeline? Well, compared with methods that do a simple RL to maximize toxicity likelihood, or with models that do supervised fine-tuning on a data set of attack prompts, the prompts discovered by this diversity-seeking method, first of all, favor an optimal trade-off on the Pareto frontier between toxicity of the prompts, so likelihood of them actually being good attacks, and diversity, meaning variety in some semantic space of the attack prompts that we discover. Where we see, for example, that supervised fine-tuning, where we fine-tune the model on a data set of attack prompts, will give very diverse prompts, but ones that you don't generalize well, so they're not actually that toxic. While RL algorithms like reinforce, which try to maximize the toxicity reward, will almost always induce a toxic response, but won't be very diverse. So they'll find a mode of very similar toxic prompts and just generate them. We see as well that the diversity that we get from the attack prompts we discover in this way seems to be helpful for safety tuning. So in this chart, we see this. So along the columns, so each column is one way of discovering attack prompts. So with each way of discovering attack prompts, we can safety tune the target model to try to refuse those prompts. And we can see if a model that's safety tuned using attacks discovered by one method can bypass the defenses of a safety tuned model that is safety tuned on attack prompts found by another method. So we see that most methods fail to bypass the defenses of models safety tuned using defenses safety tuned from attacks using attacks found by other methods. On the other hand, with the diversity seeking approach that I've described, we are both robust to attacks discovered by other methods, and fine-tuning using attacks discovered by the diversity-seeking method is robust to attacks from other methods, and vice versa. So this trade-off of diversity and reward maximization does the trick. What I think is especially interesting and I see as an advantage of the Bayesian approach, is that when we discover attack prompts in this way, targeting one victim model, we transfer very well to other victim models, even ones of a completely different architecture. On the other hand, other methods, especially the ones which tend to mode collapse, like PPO and reinforce, transfer very poorly to other target models. I should note that PPO actually fails to discover a single novel attack prompt, even for the original base language model, target language model, not to mention transferring to others. Good time to stop for questions on this before moving on to the final part, please.
Where is the diversity coming from?
So let's compare, for example, reinforce. The question is, where does diversity come from? So let's compare, for example, reinforce with GFloNet or Maxent RL fine-tuning. In reinforce, we try to maximize toxicity reward. On the other hand, here, the thing we try to optimize for is a combination of, has an entropy regularization term. So we aim to sample, equivalently, the product of the toxicity reward with some naturality score. So even if we're just sampling proportionally to the toxicity reward, we would not just find the mode, we'd sample other things with high reward. Reinforce, on the other hand, even on the same reward, will, if trained to optimality, collapse with a single prompt which has the highest reward. Supervised fine-tuning, on the other hand, will be kind of too diverse and not generalize well. Great. So now to the final part. I have 10 minutes, which will be somewhat more speculative. So far I've talked about how to do inference of latent variables which have the form of text, using a language model to sample language, but to sample it from a different distribution than the original model. But what about extracting more structured knowledge from foundation models like LLMs, which is otherwise inaccessible? So let me make an analogy with vision. So in computer vision, there's this principle that recognition or understanding of a scene is inverse graphics. So what does that mean? Well, graphics is when you have some object represented, well, one instance, I don't know, you have a 3D object represented as meshes and you render them into 2D. Or when you have an object-centric representation of a scene and you superimpose the objects to make a picture. Recognition, on the other hand, is inverse graphics, meaning that you see the image and you have to figure out what that thing was that was rendered to create the thing you see. Now, this is an old idea in vision, and there's a survey paper a long time ago which discussed this principle, which I recommend. And such an approach requires us to impose a generative model to specify how the thing we want to render, the latent, is transformed into a 2D picture. And then scene understanding is inference of the latent variables in that model that we've set. Here's one example. If the latent variable is a little graphics program, which like Turtle Graphics that or something that can do some primitives like lines and rectangles and simple control flow, then we can try to take an image and parse it, meaning infer what program generated it. So in this way, we recognize the latent structure in an image, and we can generalize. So we can, for example, change the parameters to extrapolate in the image space by modifying the latents in the latent space. So what would the analog of something like this be for language, and why do we need it? Well, we may want to understand some latent structure that is responsible for a large body of text, like world knowledge, causal structure, and so on. That's implicit in a corpus, or in the corpus that's been compressed into a language model. And why do we need it? Well, there are lots of applications of symbolic world models, for example, for planning. Here's a diagram from recent work in which a vision encoder of a scene and a text encoder which can reason in language cooperate with the aid of a causal transition model. So on some high-level latent variables representing the state of the environment, to plan through a sequence of decisions which aim to modify the latent state to eventually reach a goal. So symbolic world models, for which language models are good sources of common sense or world knowledge, are something worth studying. Now, language models as symbolic knowledge bases, that's an old idea. So there's this kind of notorious hypothesis that language models are knowledge bases that can be queried by infilling or just by left-to-right prompting. Of course they can. Yes, if you ask, if you want to know what is the capital of France, we know that it will fill it in with Paris. On the other hand, such models have no guarantee of consistency. For example, if we want to prompt for a causal structure, which we know is acyclic, this is a simple, this is a little game I played this morning with GPT-4. If you ask the sequence of 3 prompts, it gives yes to each. So the anger of Zeus causes stormy weather, which causes destruction, and destruction causes the anger of Zeus because he wants humans to do good in the world and not to destroy. So just with simple prompting, it's very hard to maintain self-consistency or consistency with some constraints, such as that we want to discover a causal model which actually is acyclic and is something we can then use for downstream planning. A question?
The real world does have cyclic causal models.
Well, what is the causal? If you say causal model means Bayesian network,
If you insist,
then
but the real world causes are cyclic.
Yes.
If you project them into language.
They're cyclic because they go forward through time. But suppose you wanted to impose a constraint, like you want acyclicity or sparsity or something like that. You can't do that just by prompting. In addition, relevant to safety, it's very easy to discover attacks on these sorts of prompts, to find ways to make them give the wrong answer or to poison the data to make them give the wrong answer to a particular prompt or prompts on a particular subject. So no guarantees. So how do we instead turn text to a symbolic or logical form? This is the problem of classical semantic parsing in NLP, where we have a text and we want to convert it to a form to something in a formal system. So some semantic parsing models are indeed probabilistic. So they assume a probabilistic model which takes a logical form, so which may be a causal model, it may be just the target of semantic parsing, something in logical form and converts it to surface form. And we want to model the posterior, yes. I see 5 here. That clock is 3 minutes fast. So then parsing the distribution modeled by a language model, in a sense, would be extracting the latent structure which is responsible for that distribution. So what do we want to parse into? Well, in semantic parsing, it's typically a dependency graph or some form of lambda calculus. Now, that's not the problem I want to study. In fact, some quick examples. Language is quite odd, and if we want to parse it into first-order logic, we encounter problems. I probably don't have time to discuss all these examples, but there are bagels outside the workshop room if you want some, and if you don't, then they're not there. They deployed the model and performed some tuning. It's very different. They performed some tuning and then deployed it. So language is very hard to translate to the most naive forms of logical systems. But perhaps if we translate to something probabilistic like causal models, then we have a chance. Now, I should say there are logical systems which handle this sort of thing, but probably it's hopeless to try to go for one that's universal for all the things that we try to express in language. We just want a formal system which is useful for what we want to do, like expressing the values of the users or expressing the guardrails with respect to which we aim to plan. Now recall, language models can parse text into symbolic structures fairly well, but they're quite bad at doing consistent reasoning in causal models, in simple graph models, and executing algorithms which can be tractably done just by writing a program with no training of an LLM. So the conclusion from this is we should extract formal structures from LLMs by performing structure learning, by amortization, rather than asking the LLMs to reason within those formal structures, which they're not so good at. So how would that work? Let's take the example of trying to distill a language model into a causal structure. So here are 2 intractable inference problems which we're trying to solve. We could use the LLM as a prior. So likelihood of sampling a causal graph should be proportional to probability of some description of that graph under a language model. So a language model is the prior, maybe multiplied by probability of some observed data given that graph. So this is the typical Bayesian structure learning setting, except the prior is not something simple, something simple and tractable as it usually is, but a language model description of the graph. So the world knowledge in the language model acts as a prior over the symbolic structure. Another thing we may want to do is use the language model as a source of likelihoods rather than a prior. So the likelihood of a given graph explaining the data, we don't actually observe the data, but of a given graph being extracted should be proportional to the likelihood that data generated from that model is likely under a language model. So if we assume that the language model understands how, say, state transitions in an environment work because of its world knowledge, we should just find the causal graph whose predictions are most consistent with those likelihoods given by an LLM. So both of these problems amount to a form of elicitation of latent structure knowledge that is responsible for the distribution expressed by the LLM. Right. Some conclusions, right on time. We've seen a couple of synergies between Amortised Inference, which provides structure and the ability to reason in a formal system, and foundation models, LLMs, which give us grounding in big data and data-driven priors. And amortized inference techniques, like ones using maximum entropy RL, allow us to extract inaccessible knowledge, whether symbolic or whether high-level symbolic or language-like, to induce explainability and structure in our answers. This can have applications to all sorts of things relevant to explainability and interpretability, and in scientific discovery, which I think we'll hear in the next talk. There are 3 probable prerequisites for a robust and safe large-scale AI. I think many would agree. Some form of symbolic reasoning, some form of uncertainty awareness, or Bayesianism, if you like, and grounding in large-scale world knowledge, because we can't hope to specify everything through human-imposed rules. And so my answer is that for that we need to do symbolic reasoning and do so in a probabilistic way, and to probabilistically extract the symbolic structure from language models. Here's a summary of all the 3 takes I've given, contributing to the list of this day and a half. And I'll finish there. Questions?
We have time for one question. Yes.
Thanks for the talk. I'm curious, how do the applications you give in out-of-distribution detection, small sample inference, robustness, how do these just not get run over by the bitter lesson and just getting more samples?
How does this not get run over by the bitter lesson and giving more samples? So the bitter lesson refers to the fact that, well, most broadly, it's better to train a bigger model than to do something more clever in the end. Well, I would say this. When we talk about RL-based inference algorithms, they have the property that as the inference model gets bigger, the approximation to the posterior gets better. So why don't we turn the bitter lesson on its head and train very good approximators of Bayesian posteriors? And that'll be our clever thing, which also gets better as the model scales. So let's train large-scale samplers of latent symbolic structures, of reasoning chains, and so on, and use and like riding on the lessons of how to scale LLMs in the training from data setting. And that way, like, what do we lose? The model scales, and we become better approximators of the Bayesian posterior. These things can scale along with models, and there's no adversarial game between the generator and the supervised language model and the posterior.
Also, we don't have infinite data nor infinite compute, so if we can use our data in a smart way, we can get better sample efficiency, which is going to mean better generalization. We don't need to make very strong assumptions for that to happen. Just like everything that Kolya talked about is using large neural nets that don't make any parametric assumption. All right, let's thank Kolya again.
Thank you.
So we have a break until 4.